Welcome back to Aurora Tech Channel. Today, I will be reviewing this Carvera Benchtop CNC from Makera. Let's take a look at the features of this machine. It has a 6-bay auto tool changer and a 200-watt brushless spindle with a Hall sensor that provides feedback to the controller software. For the motion system, the X, Y, and Z axis all use ball screws instead of the lead screws you see on other budget CNCs and 3D printers. The X and Z axis use 15mm linear rails, and the Y axis uses 25mm linear rods. The stepper motors on all axes are 30-watt closed-loop servo motors. The machine weighs around 110 pounds, and the structure of the machine is made by CNC using solid aluminum and sheet metal. The bed is a 10mm thick aluminum bed with a replaceable water-resistant MDF bed on top. The working area is 360 by 240 with a 140mm Z height. You can pay an extra $300 to get a 4-axis, which I will also test out in this video. As for the other features, this machine comes with both a manual probe and auto probe sensor, which supports auto leveling. There's a built-in vacuum, a dustbin, as well as a 2.5-watt laser module for some light engraving jobs. At the price of $4,000, I can't see any direct competition for this machine in the market. The closest machines I can find are the Carvera 3D Nomad 3, which costs around $3,000, but it doesn't come with an auto tool changer. There's no dust collection system, no laser module, no auto probe or auto leveling, and it just uses lead screws and linear rods instead of ball screws and linear rails, and by default, it only comes with a 70-watt spindle. The working area is also much smaller at 200 by 200 with an 80mm Z height. Another machine that is similar to the Nomad 3 is the Phantom Tools Desktop CNC, which costs $6,500. It comes with a slightly more powerful 250-watt spindle, but it has no auto tool changer, no auto probe or auto leveling, no dust collection, no laser module, and it just uses regular lead screws and linear rods. The working area is also smaller at 178 by 229 with the 83mm Z height. The only desktop or benchtop CNC that comes with an auto tool changer that I can find is the Roland MDX50, which costs over $10,000, but only comes with a 50-watt spindle that is mainly used for PCB milling. If you need a 4th axis on this machine, it costs another $4,000, which is the same price as this Carvera CNC machine. Overall, I'm really excited to test this out. I would like to thank Makera for sending me this machine to review, and with that, let's get started. The machine comes in one piece, so there is nothing to assemble. All you have to do is remove the protective materials and loosen a few screws to remove some mounts, which are used to secure the components. Besides the machine, we also have a toolbox with a few different types of mounting brackets, screws, end mills, and some other tools. Inside the accessories box, there are some extra collets, including 4mm, 6mm, 1/8 of an inch, and 1/4 of an inch, as well as safety goggles, laser goggles, a filter, and some spare parts. The machine comes with a replaceable water-resistant MDF bed. On the right side of the bed, there is a 6-tool bay for the auto tool changer. We also have a small dustbin for the built-in vacuum, and on the right side of the spindle, there is an air assist nozzle that allows you to connect a compressor. On the left, there is a 2.5-watt laser module. This thumb screw is used to adjust the height of the vacuum dust shoe. The spindle has its own cooling fan with a dust filter, and the maximum RPM of this 200-watt brushless spindle is 15K RPM. The lid of the machine is supported by 2 gas springs, so it won't just drop without pressure on it. There are also seals on all sides of the cover. There are 2 mounting spaces on both sides of the machine, and depending on your working area, you can mount a tablet on the machine with the included mount. Okay, let's download the software from Makera's website. It seems like they're also launching their own CAM software soon, but for now, only the CNC controller is available. I will download that and use my own Fusion 360 as my CAM software, and I will download and install the Windows version. You can either use a USB or use Wi-Fi to connect to the machine, but I actually ended up using both. I mounted a Windows tablet on the machine to connect to using a USB, and I used the Wi-Fi to connect to my main PC for when I needed to transfer files and monitor the job. I will show you more of this later when I start some jobs. Let's home the machine and then try moving the X, Y, and Z axis. Everything seems fine, so I will put some tools into the tool changer bay and get ready for some jobs. According to the manual, the default orders of the tools are as in this diagram. All the example jobs in Fusion 360 tool library will follow this order as well, so I will just stick to it. I will use the test file to make sure the auto tool changer is working and select the atctest.nc file. As you can see, there are just a few lines of G-code. T0 is the probe, and you just need to change the tool number and the ATC will work according to these instructions. So, if your CAM software doesn't support ATC, you can simply add one line of G-code to let the machine change tools before the next operation. Okay, let's run the job. It starts by grabbing the probe, setting the tool height, moving on to the next tool, and setting the tool height. The ATC is working fine, so we're ready to start the first job. Other than the instruction manual, there's another guide for a few examples. By following these example jobs, you will have a better understanding of how this machine works. Let's start with the LED light project. This project contains a few parts, including the acrylic engraving, the ABS base milling, the PCB engraving, and aluminum milling. I will start with the PCB, so first, I'll cut out one of the waste boards to match the size of the PCB board. Then, put the waste board under the PCB to protect the bed, as we need to run a contour operation to cut through this PCB. Secure them both with the brackets, open the G-code file, and enter the offset numbers and other parameters following the example's guide. The X and Y offset is the distance between the mount at the corner. Scan margin will do a preview scan, like what you do on a laser engraver to draw the frame of the working area. Auto Z probe will detect the stock height, and auto leveling is optional, but it's still recommended for engraving jobs like PCB that require high accuracy, as even the PCB is not flat, so the Z motor will move up and down to compensate for that. I will just follow the instructions and start the job. It starts by grabbing the probe to do a scan. There's a tiny laser dot, but it's hard to see on camera. Then, it will probe the height of the material, followed by auto leveling. Next, the ATC will grab the engraving bit, set the tool height, and start engraving. The vacuum of the machine automatically turns on when the spindle starts, but I forgot to adjust the height of the shoe duct, so there's not much copper dust that can be collected. But I'll just let this job finish so we can get an idea of how it looks without using the vacuum. After a while, it changes to a drill bit to drill some holes in the PCB. And finally, runs a contour operation to cut out the PCB. Okay, the job is finished. I will home the machine and use my own vacuum to do some cleanup. Remove the PCB, break the tabs, and sand it down using one of the sanding blocks that came with the machine. As you can see, the lower left corner wasn't done perfectly and some copper is left over here. I just checked the examples guide and it seems I missed 2 screws at the corner bracket to secure the lower left corner, so I guess that may be the reason why the corner lifted while the machine was working. I also didn't lower the dust shoe, so I will fix these mistakes and restart the job. As you can see, I added another 2 screws to secure the lower left corner, and I also manually turn off the LED lights so the preview scan is easier to see. The laser dot is a little bit dim, so it still isn't that obvious in some areas. I also lowered the dust shoe, so let's see if we can get some improvements. This time, the vacuum works pretty well. Most of the copper dust is collected, and we can clearly see what the machine is doing. The lower left corner is also secure as it is no longer lifting, so we should be able to get a much better result this time. Okay, the job is now done. The vacuum collected most of the copper dust and basically no cleanup was required. Compared to the previous one, the lower left corner doesn't have the same issue anymore and this PCB was done perfectly. Next, I'm going to use an ABS board to make a base. Cut a waste board that's the same size as the ABS board to protect the bed and secure them both using the brackets. Follow the parameters on the example guides and start the job. As I found the ABS board is actually large enough to make 2 bases, I will make one without lowering the dust shoe and see how messy it can get. It seems the machine is cutting this ABS aggressively and removing material pretty quickly. After a while, it reaches the bottom and you can see the debris of the MDF wasteboard. Then, it changes to the engraving bit to make some chamfers for 4 screw holes, and after that, changes back to the 25mm long flat end mill to run a contour to cut the entire base out. Without the vacuum, the inside of the machine is pretty messy, but I will just clean it up with my shop vacuum. Use the mini saw that comes with the machine and cut off those tabs. It looks alright, but I will now try to connect my shop vac to the machine and see what the difference is. I 3D printed an adapter for the shop vac, but remember to switch the hose to the second from the left hole to connect to the external vacuum. This time it looks much better. I think 98% of the debris was collected, and compared to the previous attempt, the cleanup should be much easier. The part looks better, though the difference is not huge, but it definitely looks cleaner compared to the other one. Then, I will make a simple button using this 100 by 100mm and 5mm thick board of aluminum. I also turn the vacuum off as I want to see how it cuts the aluminum. Although the debris covered the entire part, the part was still successfully cut out. I will do more tests on aluminum milling and push this machine to its limits to see how aggressively it can cut aluminum. Up next, I will do the last part of the LED light example project, which is the acrylic engraving and cutting. Run the example file and follow the parameters from the example guides. The pre-scanned dot is almost invisible on this acrylic. I will try to switch off the LED lights, and it looks much better. This time, I will use the built-in vacuum as I don't think working on this acrylic will be as messy as ABS, so the built-in vacuum should be enough. After the engraving is done, it changes to a flat end mill to run a contour to cut out the board. The dust connection seems to be working very well. Most debris is collected inside the dust bin, and after the job is done, the inside of the machine is still pretty clean. The engraving result looks alright, but it will look much nicer when I put everything together. Then, I will try out the laser module. Since it's just a 2.5 watt module, it should be good for only laser engraving. Let's run the example file, which is the portrait of Audrey Hepburn. The result looks pretty good, or is at least much better than I expected. The good thing about the laser module on this CNC is that it can auto-probe the Z height, so you don't have to adjust the focal length like you have to on other laser engravers. I will try one last example job before starting my own jobs. For this job, I will install and test the fourth axis. According to the instructions, I should rotate it and let the corner face up, but since it's just a rotary roller and will take off most of the material on the surface, I don't think this will make any difference, so I will just align the flat side on top and see what happens. To use this fourth axis, we need to remove the dust shoe and the dustbin, as otherwise, the motor on the fourth axis will bump into the dustbin. Let's open the first roughing file and start the job. Then, I will open another finishing job and the machine will change to an engraving bit to continue. Okay, the job is now done, so let's do some cleaning up. There was an error in the G code that caused damage to one of the ears, but the other one was fine. Besides one of the ears, the nose is also flat, which I guess is why the manual requires rotating the corner of the stock to be facing up, so there will be enough material for the nose. I asked Makera about the damaged ear, and they said they've already noticed this issue, and all the new machines will include an updated G-code file. Considering that this model is even smaller than a 3D Benchy, the level of detail on this tiny model is quite impressive. I will now go to Fusion 360 and do some more tests. As Makera provides the machine and tool profiles for Fusion 360, just go to the Manufacturer workspace, select Manage, and Post Library. I've previously used the GRBL and Mach 3 with other machines, but I will now import the Carvera profile. Next, go to Machine Library and import the 3-axis and the 4-axis machine profile. Finally, go to Tool Library, create a new folder, and import 3 libraries. Okay, the setup for Fusion 360 is now done. I will draw a simple sketch in the Design workspace and extrude it to make a plate and run some engrave, bore, pocket, and contour operations. If you want to learn more about the basic CAD of Fusion 360, I have a series of short videos for beginners. To generate the G-code, we need to go to the Manufacturer workspace. First, we need to create a setup. The height and width will follow the actual material size, and in my case, it's 150 by 100 and the board is 10 millimeters thick. As the board is larger than my design, I will just set the X and Y offset from the center to 10 millimeters. The stock point is set to the lower left corner to match the default corner bracket. The machine would be Carvera 3-axis, and that's all we need in this setup. As you can see, I've set up 4 operations and used 2 tools. For the engraving, I selected tool number 2, which is the same engraving bit I used to engrave the acrylic and PCB. I will use the parameters for softwood, MDF, and epoxy. The geometry to engrave would be the text. I will set the height to start from the stock top to stock top with a -1 millimeter offset, which means the bit will cut down 1 millimeter from the top surface. As the epoxy board is soft, we don't need multiple depths, and I can engrave this 1 millimeter all the way down. The second operation is a bore. It will cut through the entire board to make these 4 holes. The tool I selected is the 25mm flat end mill using the softwood parameters. The geometry would be these 4 holes, and the height will start from hole top to stock bottom with a -1 millimeter offset, which means it won't stop cutting until it reaches 1 millimeter below the stock bottom. We also don't need multiple depths, as it should be able to go straight down with the bore tool path. The third operation is a 2D pocket. The tool is the same flat end mill from the previous operation. The geometry selected is the slot here, and the height will start from the top of the stock down to the bottom of the contour. If you want to do a roughing operation, you can leave a few millimeters of stock for finishing, but as the epoxy board is soft, I will just cut it down in one pass. The final operation is a contour. The tool is the same flat end mill, the geometry will be the outline of the design, and the height will be the same as the bore. As we want to cut through completely, it will be from stock top to stock bottom, -1 millimeters. As it's going to cut down 10 millimeters in one pass, I will use multiple depths this time and set the maximum depth to 3 millimeters. Okay, let's run a simulation. It looks good to me. The bore and contour operations both cut through completely, and the total machine time is a little less than 8 minutes for all 4 operations, and we need 2 different tools. Let's select Post-Process and export the G-code. After the epoxy board is secured, we can start the job. I didn't lower the dust shoe, so can only collect some of the debris. It's easier to clean up than the ABS. The result is also pretty nice, and all operations ran exactly like what we saw before in the simulation. Next, I will try some aluminum cutting. As this machine only comes with a 200-watt brushless spindle, it sounds like it doesn't have a lot of power, but since the machine is super sturdy and heavy, I think this part would help a lot with aluminum cutting. The manufacturer recommends setting the step down or the depth of cut to 0.1 millimeters, but I will make 10 slots and try starting from a 0.1 millimeter depth of cut and go all the way to 1 millimeter to see how far I can push it. I purchased a low-profile CNC vise for this machine, so I don't have to cut a wasteboard every time. And we can now upload the file to the machine. Select the file and enter some parameters. I measure the offset manually from anchor 1. I will do scan margin and Z probe, but I will just skip auto leveling as I wanted to start 1 millimeter outside the edge of the aluminum plate to get a better filming angle, so the probe should not be able to probe that area. After the engraving is done, it will change to the 12mm flat end mill, starting with a 0.1 depth of cut. As I lower the dust shoe, most debris can be sucked into the dust bin. Okay, the 0.1mm depth is done, so let's go to the 0.2mm depth. Then the 0.3mm depth. Even with a 0.6mm depth of cut, it still looks pretty good. Finally, it's going for a 1mm depth of cut. The chip is much larger and it sounds a bit louder, but everything still looks good to me. As you can see, most debris goes inside the dustbin and the inside of the machine is still quite clean. After some easy cleanup, all slots from 0.1 to 1mm depth of cut actually all look good. When looked at from a closer distance, they still look alright. I think using 0.6 to 1 for roughing and 0.3 for finishing on aluminum can still deliver pretty presentable results with this machine. After that, I also ran a few bore operations to cut through this 5mm aluminum board. There's no big difference in the depth of cut from 0.3 to 0.6mm, and all of them are pretty clean. Then, I ran another pocket and bore operation using 0.5, 0.75, and 1mm depth of cut. I turned off the vacuum on the 1mm to see the chip size. This 200-watt spindle can cut out pretty large chips from the stock. When I checked the accuracy of this 20mm square, the 0.5mm depth is right on spot, the 0.75 depth is almost perfect, and the 1mm depth of cut is only a tiny bit off. I will do a final test on aluminum to cut off this plate using a 1mm depth of cut. I also turned the vacuum off as I wanted to see the chips fly. The cut looks alright. As the part is outside the vise, it vibrates a bit more than the pocket and bore operations, but doing a 1mm depth of cut on aluminum is still pretty impressive for this 200-watt spindle. Finally, I will also test out the laser module. I will make a simple image, open it using the free LaserGRBL, set the mode to black and white dithering, set the speed to 2000 millimeters per minute, and use M3 constant power. Just save it as a G-code file like you would for a regular laser engraver, but you need to add M321 at the beginning to switch the machine to laser mode, and add M322 to turn off laser mode when the job is done. The result seems alright, and the laser is usable. Okay, let's talk about the pros and cons of this machine, starting with the pros. 1. The auto tool changer runs flawlessly. I didn't run into a single error or misalignment issue during the entire test. Even when working with the 4-axis without the dust collection system, when the debris is all over the place, it doesn't affect the auto tool changer. 2. The machine uses simple G-code to control the tool changer. Even if you are using a free version of Fusion 360 that doesn't support multiple tool changing, you can just export multiple G-code files and combine them using a text editor and add one line of G-code to change the tool. 3. The dust collection system works pretty well. All you have to do is adjust the thumb screw to drop it down, so it can trap most of the debris and suck it to the dust bin. Or you can connect it to an external shop vac for even more suction power. 4. The 200-watt brushless spindle works very well, and I was really impressed by the aluminum cutting results. If you've watched my previous videos, I've tested out some cheap 500-watt and 800-watt spindles from AliExpress, and those spindles don't even come close to this 200-watt brushless spindle in terms of both cutting speed and accuracy. I have another larger CNC router with a 2.2 kilowatt spindle, which is much more powerful, but the accuracy is also worse than this Carvera CNC. 5. The Wi-Fi feature is convenient. I actually mounted a Windows tablet on the machine and connected it to the USB port and then connected it to my computer using Wi-Fi. They can show the readouts and operation at the same time, which is pretty awesome. It provides a smooth workflow too. After I export the G-code file from Fusion 360, I can just upload the file from my main PC and then use the tablet to enter the parameters and offsets and start the job. Now for the cons. 1. The preview red dot from the probe is too weak to the point where I can't see it at all, especially when the LED lights of the machine are on. So maybe the machine should turn off those lights when the preview scan is running, otherwise that tiny dot is really hard to see. 2. When using the 4-axis, as the shoe dot will affect the tool head and the 4-axis frame will bump into the dustbin, you can't use the vacuum, so the chips are flying everywhere and even cover the tool bay. It would be better to create an enclosed box for the tool bay and flip it open when tool changing is required. 3. There isn't a duct for the smoke exhausting for laser engraving. The machine stinks for a while after engraving, and the laser module is also quite weak. But as it's a CNC machine, I would consider the laser module to just be an extra feature, so I can live with this, and I would probably use a real laser engraver when I actually need to do laser engraving or cut some wood. 4. The upload file speed is slow, especially when the file is larger than a few megabytes. Using Wi-Fi to upload a 2.5 megabyte file took 3 minutes, and using a USB is even slower, but Makera did say that they would fix this in the future firmware updates. Besides that, I do have a few suggestions for Makera. 1. Release an iOS app and release their own CAM software as soon as possible, as this will be more convenient for new users who don't have any Fusion 360 experience. 2. Include a low-profile vise with the machine and set the mounting position to anchor 2 by default. I bought this from Amazon for around $70 and it works pretty well. 3. Add more accessories that are available for purchase, such as the replaceable MDF bed that mounts on top of the aluminum bed, the dustbin, filters, and some end mill packages at an affordable price. 4. Add a high-power spindle version for those who mainly use this machine for metal milling. 5. Add a safety feature to avoid manually moving to the tool bay if the Z position is too low to keep from crashing into the tools. 6. The tool should be automatically dropped after the job is finished. This would be safer for removing the part or doing some cleaning up with the vacuum. In conclusion, there's no other competition in the market that comes close to this Carvera machine in terms of specs and value. You can't find anything at the same price or even 60% more expensive that comes with an auto tool changer, thick linear rails, ball screws with a super heavy 110-pound sturdy frame, built-in dust collection, auto probe, 4-axis, and all the other features you saw in this video. I really enjoyed testing out this machine, and I hope you can find this video useful. If you are interested, I put the link to the official website under the description. That's it for this video. Thank you for watching, and I will see you next time.